convergent boundaries. The plates are coming together. In this case where one plate is going under another, you've got to have that plate going down be a slab of oceanic crust. There can be two continents that collide, but they are just going to cause a big folded mountain chain like the Himalaya or the Appalachian Mountains. So most of our convergent plate boundaries, though, you've got some old oceanic crust going underneath either younger, more buoyant oceanic crust or continental crust. So the plate that is going under is said to be subducting under the overriding plate. Okay, so the downgoing plate is going to be old, dense oceanic crust. It's going to bend down into the mantle of the other plate, and that is going to promote melting because the downgoing plate is bringing with it water that has saturated the upper part of that downgoing plate, and we have what's called flux melting. Flux melting means it's going to lower the melting temperature of those rocks, so when they get down there, they're really hot and they're wet and they melt. At the convergent plate boundary, there is going to be lots of earthquakes. So this diagram shows right here as the plate goes down, there's a cluster of earthquakes. That plate is cold before it goes down, so it is going to be bending and breaking as it goes down into the subduction zone. So all of that, these dots are more of those earthquakes. Once you get deep enough, the downgoing plate is going to deform plastically. It's no longer going to break in a fault and release that energy as an earthquake. The trace of earthquakes going down into a subduction zone is called the Wadati-Benioff zone. It's recognized as the pretty consistent pattern of earthquakes at a subduction zone. All right, features of the subduction zone. Looking at the block diagram, starting at the right side and going to the left, the plate is going down and is going to hit the trench. The trench is a topographic low on the sea floor, so it's going down into the trench. Going right along the topography here, the next thing is the accretionary prism, and I have another slide on it in a second. But as the plate goes down, like my sweater here, it's going to scrape those sediments. And so this would be an accretionary prism. It's accreting, scraping off sediments off of the downgoing slab, and they tend to fault like that, kind of in a fan shape. The other side of that, there is a four-arc basin, just the scraped off sediments, and then another basin. And then on the continent here, there is a continental volcanic arc. So the downgoing slab gets deep enough, it's going to get hot, it's bringing water with it. Flux melting causes magma to rise. That rising magma may pool in a magma chamber, but eventually as gases build up, it's going to make an explosive volcano over here on the land. The convergent boundary is marked by that trench, and then on the other side of the trench, the accretionary prism. So here's a, I don't know, scraper vehicle, scraper, tractor, I don't know, pushing up sediment and making that, I did it with my sweater, that accretionary prism. So that is pushed up. It may be pushed up above sea level. There are some mountains like the Olympic Peninsula in the Pacific Northwest is an accretionary prism. The island of Taiwan also is part of these sediments from the scraping off of at a subduction zone. All right. The slide before showed a downgoing slab of oceanic crust and an overriding slab of continental crust. In this diagram, we have oceanic crust going underneath more oceanic crust. When that happens, we still get volcanoes, but instead of forming a giant mountain chain, we're going to form an arc of volcanoes, and they're going to be islands. So here is a volcanic island arc, and they are going to form above. They're going to form within the overriding plate above that subduction zone. Transform boundary. So a transform boundary, we used the same block diagram before. You have plates going side by side. There's no consumption, there's no production of oceanic crust, there's no volcanism, but there will be earthquakes. A transform boundary that in the United States is the San Andreas Fault System. It cuts through Mexico and into Southern California. There's a bend in it here around LA, and it cuts up through San Francisco. And then as we get to Washington and Oregon and Washington, it turns into a subduction zone where the little Juan de Fuca plate is subducting underneath the North American plate. At that point, where you have the Juan de Fuca and the North American plate, three plates boundaries are coming together in what's called a triple junction. So that is a triple junction with the San Andreas Fault, the Cascade Trench, and the Mendocino transform boundary there. So it is a fault boundary that we can trace on land. So through California, you can find the San Andreas Fault as a line and offset features across the land. Here's that term triple junction again. There's a triple junction here. Here's Madagascar. So just off Madagascar, the Indian plate, the African plate, and the Antarctic plate. This is thought to be the beginning of kind of how rifting begins. There may be some mantle upwelling and cracking in three places, and beginnings of rifting. So here's the one we looked at before with the San Andreas, the Mendocino fracture zone, and the Juan de Fuca plate and the Cascadian Trench. So triple junctions are a common feature of plate tectonics. Hotspots are going to be not at a plate boundary, but be volcanism. So there's a plume in the mantle that rises up, burns through the overriding plate, and produces volcanoes. So the one we talk about the most is probably Hawaii, because it makes a nice trace across the Pacific plate. Here's a diagram showing time. So here is time 1. We have a spot over the hot spot, mantle plume underneath the Pacific plate. The plate is moving. As it moves, then volcano number 1 moves away from the source of magma. So it's moved away. It's now dormant. And volcano number 2 is now active at the hot spot and progressing to time 3 here. Volcano 1 is way off the hot spot. It's now a seamount. So erosion of waves and currents has eaten away at that seamount. Isostasy, it's cooled, it's sunk a little bit into the asthenosphere, so it maybe you can't maybe see it above the ocean surface anymore. Extinct volcano number 2 is weathering away, and then we have active volcano number 3 that's still growing. Here's the trace of Hawaii in this view of the globe. Hawaii and the active hotspot is right here. And then as the plate moves, a new volcano is forming right now just to the south here in Hawaii. But these are all old plates, so older and older, the Hawaiian seamounts away from the hotspot. And then there is a bend in the chain, and that where it bends, we change the name to the Emperor seamounts. So the Pacific plate at some point in time was going more to the north, and now it's moving more to the northwest. That change in direction is marked by the trace of the volcanoes.